Welcome to The Explainer. Today, we're going to talk about something that sounds like it's straight out of science fiction: engines that run on explosions. And I mean continuous, controlled explosions. This isn't just a tweak to an old design, it's a completely different way of thinking about how we push things forward. For decades, the go-to solution for more power was, well, pretty simple. Just cram more fuel into the engine. But we're kind of hitting the limits of that approach. It's getting inefficient, it's getting complicated, so it made people ask a really fundamental question. Are we focusing on the right thing? What if the key isn't more fuel, but a better way to burn it? And that question really splits things into two camps. You've got the old way, let's keep refining the slow, steady burn we're used to, what the engineers call deflagration, or you've got this wild new idea. What if we could actually harness the raw power of an explosion? A real detonation. Okay, to get what's going on here, you have to realize that not all fire is the same. Not even close. There are basically two ways fuel can burn, and they are fundamentally different. So first up, you've got deflagration. Think of this as the slow burn. It's what's happening in your car's engine, a conventional jet, even a campfire. The key thing is the flame itself moves slower than the speed of sound. It's a relatively gentle push. And because of that, the pressure in the chamber actually goes down. And then there's detonation. And this is a whole other animal. We're talking about a violent, supersonic blast. The shock wave and the flame fronts are basically one and the same, and they're moving at kilometers per second. Now, here is the absolute key difference. Unlike that slow burn, a detonation gives you what's called pressure gain. The pressure doesn't drop, it skyrockets. We're talking a factor of 15, maybe even more. It's a massive instantaneous kick. Right, so when you put them side by side like this, the difference is just, wow. Look at the speed. We're not talking about a small jump. We're going from meters per second to kilometers per second. But honestly, the most important thing on this whole chart is that line for pressure. Deflagration, pressure drops. Detonation, pressure gains. That one little detail changes everything. It's the whole reason we're even talking about this. And here's why that pressure gain matters so much. It's all about efficiency. That pressure gain translates directly into getting more bang for your buck, thermodynamically speaking. So the bar on the left, the Joule-Brayton cycle, that's your standard jet engine. The one on the right, the Fickett-Jacobs cycle, that's our detonation engine. And look at that jump. Under these conditions, you're going from around 33% efficiency to over 55%. That is a huge, huge leap in performance from the exact same amount of fuel. So, okay, the theory is amazing, but how on earth do you build an engine around something so violent? How do you tame that blast and make it do useful work without blowing itself to pieces? Well, the first big idea was something called the Pulsed Detonation Engine, or PDE. The concept is actually pretty easy to picture. Imagine it like a machine gun, but instead of bullets, it's firing a rapid series of explosions out the back. You fill a tube with fuel and air, boom, detonate it, get a push. Then you do it again and again, super fast. And this wasn't just some theory on a whiteboard. They actually built one and stuck it on an airplane. Back in 2008, a test plane flew, for a little while anyway, powered by a PDE. That was a huge moment. It proved for the first time that you could actually use detonation to fly. But that flight also showed everyone the PD's biggest problem. The constant explosions, these violent pulses, created absolutely insane vibrations and a noise that was just deafening. I mean, the test was so rough, they had to shut the engine down after only 10 seconds. So yeah, it worked, but it was just too brutal, too destructive. And that failure is what led to the next, much smarter idea. Which brings us to the real star of the show today. The Rotating Detonation Engine, the RDE. Now this is where things get really clever. See, the genius of the RDE is that it solves that vibration problem by making the explosion continuous. Instead of a series of separate bangs, bang, 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 the RDE creates a single detonation wave that just keeps going. It literally chases its own tail inside a donut-shaped chamber, spinning around and around. And that continuous motion is what turns those violent pulses into a smooth, steady push.
The cycle itself is almost beautiful in its simplicity. So you're constantly feeding fuel and air into this circular channel. The detonation wave, once you get it started, just spins around and around, eating up that fresh fuel mixture in front of it. And as it goes, the high-pressure exhaust gets shot out the back. Simple, continuous, stable thrust.
And it's really hard to wrap your head around just how intense this is. That wave is whipping around that channel at supersonic speeds. It's creating thousands of these little pressure spikes every single second. Think about it like a tiny supersonic hammer hitting the engine, thousands of times a second. That's the incredible constant force that makes an RDE go. Okay, so the concept is awesome. It's elegant, but how does it actually stack up in the real world? Let's get into the nitty-gritty, the real promise, but also the very real problems. And this is the crucial part. This is not just theory. They've run tests. In one really interesting experiment, they took a helicopter engine, pulled out its standard combustor, and dropped in an RDE combustor. And when they ran it on hydrogen, they saw a 5 to 7% boost in efficiency compared to the original engine running on regular jet fuel. That's not a simulation, that's a real measured gain. So, if it's more efficient, potentially simpler, what's the catch, right? Why isn't this technology on every airplane and rocket already? What's the holdup? Well, the engineering challenges are just massive. For starters, you've got combustion stability. That spinning wave has to keep spinning perfectly. If it flickers or dies, so does your engine. Then there's cooling. The amount of heat this thing generates is astronomical. A huge part of the problem is just figuring out how to stop the engine from melting itself into a puddle. And finally, you have to be able to start it reliably. Getting that detonation going perfectly every single time is no small feat. But even with those huge hurdles, the potential payoff is so big that labs all over the world are in a race to crack these problems. So let's imagine for a second they succeed. What does a future powered by RDEs actually look like? Well, the vision is a total paradigm shift. Since RDEs basically create their own pressure, you don't need those huge, heavy, and super complex compressor sections you see on today's jet engines. You could shrink them way down, or maybe even get rid of some of them. What you end up with are engines that are way smaller, lighter, and have fewer moving parts, all while being more powerful. It's kind of the holy grail of engine design. And this quote really drives the point home. You know, a modern gas turbine might have, say, 14 different stages just to compress the air, but an engine running on detonation, it might only need half that. Think about that. You're cutting the complexity and the weight down dramatically. That's not an improvement, that's a revolution. So that leaves us with this incredible thought. In the future, when we look up at the sky, will we hear the familiar high-pitched whine of a turbine, or will we hear the deep, contained thunder of a spinning detonation? This tech isn't just about changing engines. It could change the very sound and feel of flight itself. It's a powerful idea, one that's definitely going to shape the next chapter in aerospace. Thanks for joining me on The Explainer.